Okay. So this is all about the next week. So homework 4 deadline, and this is 2 weeks from today, Monday, final product team notification. You have all anyone who didn't find the team member yet? Please put it in the Piazza. It should be 3, but if you have a special reasons, uh, then we can discuss. You can. Well, as far as I know, we are 21, right? So if you made a two people team, then you also need to talk with the other teams. Anyway, let's move on. So seems like everyone get the team. That's great. So far what we learned is basically 4 things. It's a bit disappointing, right? It's just a 4 topic. One is the kinematics, order and inverse. And we also learned the 3D orientation. We learned how to use the Jacobian. And the calculation of the Jacobian is actually a bit, demanding work. You need other joints and the dynamics. So today we're going to study feedback control. And what I think everyone kind of familiar with this term, right? Feedback, control. In robots, normally the control is the actuator, so motor, you do the control to do something, but what's the definition of the feedback control? Have you heard about it? Yeah, what is the definition of the feedback control? I mean, sometimes it's hard to, memorize the definition because it's too familiar. So once you're too familiar with a certain term, you forget about what was it, how to officially define it. So feedback controller is whatever controller changing the input based on the past experience. And this experience in the system is going to be sensor data. So if there is a controller, actually, whatever things, changing the input for the system based on the previous sensed data measurement, then it's a feedback control. It can be negative, it can be positive, but feedback control's idea is I see the past and I'm going to do the better job in the future. And if it worked well, then it cancels out the many unwanted behavior or error. If it doesn't work, and you cannot bring the system to the state you want to be. And it can be even worse. The worst means the system can blow out. I think you've seen the what happens when your robotic arm become a singular, but try to solve the inverse kinematics, right? You see the robot is vibrating all around, and then eventually blow out, right? So that kind of things can happen. So how you define the feedback control is a lot of work actually. But we're gonna cover only the intro part of the feedback control. I love feedback control, and there is a lots of mess and the theory. But today we're gonna focus on the PD control, what is the best PD gain, something like that. But if you want to know more about the feedback control, then there is lots of different reference. Of course, if you're more into that system, feedback control, then you can also, have the nonlinear system books this thing. But basic robotic feedback control is pretty much covered in the modern robotics book, chapter 11 and 11.1.2. That's also good reference point. Okay, let's get started. So we're going to start it from the really simple system. Just keep rotated by this level joint. Pretty much similar to your last problem of the homework 4, right? So tip going to start any positions. So angular position wise, it can be started here, but we want to bring it to the target. So aligned with a certain angle. That's the goal, right? How can we do? I mean, one obvious thing is that we can make a, kind of virtual spring. So if the spring, imagine that there is a spring, torsional spring, engaged in this first, in the revolute joint, and the neutral location is pointing target position, target angle, then it's gonna go back to that position, right? Okay, that's a one way. That's a pretty much a proportional gain. So if the control input, if you write down the equation for control input, it's going to be something like this. Okay, this is result, simulation result, and you can see it's when I plot it, and it's like this. Blue is position, angular position. This is angular velocity. This is our desired. Seems a bit different from what I want to do, right? And why? Why is oscillating not instead of doing this, right? Oscillating around this desired target angle.
It gets pulled to the desired position, but it still has velocity, so it overshoots.
Yes.
It's been pulled it back, same thing.
Back and forth, right? And there is nothing like a energy dissipator. What it means that once it has started from the potential energy, and then it has the potential energy because of the spring and deflection. What is the potential energy? The equation for the potential energy is 1 over k theta square, right? If the desired neutral is 0. So it started from that potential energy, then gonna switch back to the kinetic energy, potential energy, back and forth without losing the energy. And how should we do to lose that energy?
What's the K? KP?
Yeah, this is feedback gain, proportional feedback gain, but you can think this is virtual spring. So in this case, the equation actually say that my neutral position is theta desired, and my current position is the theta. So it's oscillating around the theta desired. Right? It makes sense, right? But you're never gonna see this kind of behavior in the real world because most of the spring, actually, in the real world, you cannot make an ideal spring. Ideal spring means that you do not lose any energy. There is no, spring like that. It means that there is a perfect spring does not dissipating any energy. So you probably think that, yeah, every time I see the spring, then it behaves like this, right? So that's the damper. And we can see the spring damper system everywhere. The tire, your car has it, and most of the spring, actually, every spring is actually spring damper system. So that's the spring damper. This is actually exactly same as proportional and derivative feedback control idea. And here, this is the equation we can use to imitate the spring and damper behavior. When you see the textbook, then you can see that theta is here, and theta desired is actually subtracted from the theta, and you see the theta that is actually positive instead of without this sign. I mean, that's also equally valid if your Kp and Kd is negative number. I prefer question. Damper taking the energy. So when you see the equation, then when the theta dot is positive, then torque is negative. And when theta dot is negative, torque is positive. So what it means that whenever a system move to the certain direction, it try to retract that system. So it actually, prohibiting this movement. So eventually it goes down to the zero velocity. Okay. Yeah, I'm talking about the Kp and Kd, right? So yes, I prefer writing the equation in this way because then I can just put the positive number KP and KD, and then always putting the theta desired in front of this theta measurement. And then why this is minus? In this case, our theta that desired is 0, right? We want to make the system becomes 0 velocity. So that's why it ends up with this equation. Okay, if I putting this KP and KD to this system, then you're gonna see the behave somewhere between this and this. Did you see it? So this is underdamped system, oscillating but eventually stop. This is overdamped system. By the way, this is critically damped system. What's the difference between overdamped and critically damped? They
Just takes longer for that overdamp than it needs to.
Yeah, exactly. So critically damped, when you see the behavior of theta, then you see the overshoot above the desired. And then as you increase the damper, this gonna, stabilize before, without, going beyond the desired. Then there must be the certain point, overshoot is just 0, right? So that's the critically damped situation. So how can we find the critical damped? I mean, there is the way to find it. But before we talking about it, let's plug in this in the dynamics. So this is the system dynamic equation, right? The homework 6. We have an inertia, we have a mass, and center of mass position is up by theta, up by c from the level joint position. And the inertia should be I plus mc squared times acceleration is torque, right? And here we can plug in that equation we just found, we just defined to the torque. So far so good. And then moved everything to the left, give us this equation. So it's mass, damping, and spring. So this is spring mass system. And probably mechanical engineering students heard about the second order system more frequently than spring damper. But basically, it's a spring damper system, second order system. It consists with a mass, damper, and spring constant. Kp, proportional feedback gain, is a spring constant. Derivative feedback gain, which is Kd, is damper. So far, so good? Okay. So there is the standard way to put this equation in the second order form. And here omega 1 means the natural frequency and zeta is damping ratio. First in-class exercise. Okay. What is the omega n? I mean, omega n is the function of the spring constant and mass. So what is the omega n? How can you define omega n? Is a problem. I'll give you 1 minute. Okay, what is it? Yeah, square root k over m, right? That's the definition of the natural frequency. What is the meaning of the natural frequency? We're gonna go in there just in a second. But everyone, fine with this definition, right? Omega n is the square root k over m. And just want to make sure that everyone is following, I mean, so far it seems kind of too straightforward and easy. So when we see this term seems related to B, which is damper, right? And damping ratio has this meaning. If it is a 0, then it's critically damped. If it is less than 1, if it is 1, then it's critically damped. If it is less than 1, underdamped. It's a larger than 1 is overdamped. And problem 2. What's the find find the zeta. Find the B of critically damped system in terms of the K and M. So what is the B at the zeta is 1? What's the B? Who I think someone missed the 2, right? Okay. So equation. So what it actually asking is 2 omega n zeta is B over M, right? And this omega n is square root K over M. So if this is 1, B should be 2 times M times square root K over M, which means that 2 square root MK. Does that make sense? And this actually give us the what's the damper? What is the damping gauge we have to use once we specify the K, right? Let's say that if the mass is 1, unit mass, if I use the K as the 100, then critically damped damping gain is 20. So that actually gives the ideal what is the proper KD gain I have to use. Of course, this is just a guideline. It's not always true in your system because system has more than just the spring and damper, but that actually giving the really good guidelines, you should then use 100 kp and 100 kd. The system going to be too damped. And I will show that it is not just the damped. Sometimes it make the system blow out. Okay, so far so good, right? And then this system is a stable. This spring damper system is always stable. Can you believe it? Right. First, we need to define what is the stable means. So stability is officially defined in this way. If the state, if the state space and the origin is stable, what it means that there is some region when the state started from that region, that it's gonna stay inside of that region. Does that make sense? Can you accept this? I mean, what it means that if you started from the certain angle, even though you oscillated, as long as that angle is bounded a certain region, then system is stable. Even though it's moving chaotically, But as long as it is inside of boundary, then it's a stable. Then you might think that's a bit different from the my stability, right? I think my stability is when I say the system is stable, then at least it need to slow down and then converge to somewhere, right? So for those of you who can complain, who doesn't like this stability definition, so we prepared another one, which is asymptotic stability. Asymptotic stability means that if you see the systems for a long time, so for long enough, infinitely long enough, then state approach to the origin. And here state is position and velocity. What it means that system going to stop eventually. So when you visualize this, then it's something like this. So it started from somewhere, but it converged to the origin eventually. Are you familiar with the state space plot? So state space plot. So control theory, control researchers so love math. So they made lots of interesting tools. State space representation is one of it. So it's something like this. So position x-axis, velocity is y-axis. Right? Does that make sense? So this x and x dot plot is actually one-dimensional system. So it's only moving forward and backward. And you can plot it in this xy plot. It is figures a bit weird then. So the figures say that if it started from here, then it converges to the origin, right? Isn't it a bit weird? Anyone can find this? This probably the most difficult question I asked them during the lecture. It's like hide and seek. You found it?
Circle.
Yeah, it's just system, but it behave like that. So circular movement is not, the weird part. There is the clearly wrong things in this figure.
If the system isn't oriented, then it just never reach the origin, it would just be in a circle around the origin.
Actually, if the system is damped, you mean the position may not goes into the x 0, right? But it depends on how large spring you have. Actually, as long as you have a spring, then it gonna goes into there. Because it's exponent.
System's gaining. But it's just not rest.
Oh, this is actually a stable system, so you need to lose the energy. But is that answer for your question?
Without gaining energy, just looking at the plot of x, the plot of x dot.
Yeah, it does not gain energy. Yeah, but this plot actually doesn't make sense. You found it?
It's assuming x and x dot are independent, but when you do the spiral going left, so x is decreasing, but it's in the upper quadrant, so.
Oh, did you understand that? Yeah, so if system is here, what it means that position is positive, velocity is also positive, so you need to move this way. So there is no spiral like this. And here, you need to move this way. So spiral, if the system going to converge to the origin, it should follow this line. I mean, the line can be different, but anyway, it should move this way. Only when it is negative, has a negative velocity, in the next step, it must move to left. Is it left, right? So that's a page plot. I mean, this is one example, good example to, to confuse what the state space plot is. Does that make sense? So if you're here, then you need to move this way. If you're here, you need to move this way. Because the only thing you control is actually acceleration. That's the mechanical system idea. Okay, Lyapunov stability. So this probably the most beautiful, simplest way to prove the system is stable. Idea is pretty simple. Definitely, the description is pretty simple. It doesn't actually say about what is the V is, but as long as you found the V satisfying these three conditions, then the system is stable. Isn't it cool? Everyone, I mean, is there anyone who familiar with already know about the Lyapunov stability? You know the Lyapunov stability. Do you know why? Do you know that can we use this Lyapunov stability analysis to prove the system is unstable?
Yes.
So, actually, no. Sorry. So if the system is stable, this is actually big theory. If the system is stable, then there should be some Lyapunov function. And this Lyapunov function has this three criteria. In the origin, it should be 0. Other than the origin, it should be positive. Time derivative of this function should be negative. That's all. The problem is, even though you cannot find the Lyapunov function, it doesn't mean that system is unstable. Maybe you just didn't find it yet. So it's actually, you cannot use this analysis to prove the system is unstable. You can get an idea, like, define the energy as the Lyapunov function and see that the energy is continuously going up. So highly likely system is unstable, but that doesn't sufficient because this only about the necessary condition. Does that make sense? So there is a lots of interesting story related to this Lyapunov stability analysis. First of all, is from the Russian control theorist. At the time they developed this algorithm method, it was Cold War, so the half of the world doesn't know about this stability. That's also interesting. And I saw the question.
It's one of my other classes, like network question, but I think it's like unstable if it's not like not stable and it's not a tractor. Right?
But that doesn't necessarily, it does not, guarantee the system is unstable. Right?
I think like the condition is also not an attractor.
What is the attractor?
I forget like the formal definition of it, but like you system is an attractor if it like fulfills like some sort if the matrix like fulfills some sort of definition.
Okay, so there is actually Lyapunov stability is not only about this one. This is the first order definition. So Lyapunov stability is actually more broadly defined. So maybe there is a way to define the system is unstable. So for instance, if you write down the state space equation, the A has the negative real world in the eigenvalue, then system is unstable. So that kind of things is possible. Using Lyapunov function to prove the system is unstable is not possible. Because you never know that there is the Lyapunov function. I heard that NASA tried to prove that their rocket control or satellite control is stable, but system dynamics is too complicated. So one researcher actually spent 1 year to find the function. So that process is not super scientific because it's like putting exponential term, sine term, cosine term, see this term is cancel out. At the end, it becomes negative. Maybe not. So then it just But that process, that 1 year process, after 1 year, he got it at the end. And then he said that I'm not going to do anything related to the Lyapunov anymore. So literally, he tried to, think about that guy's how many function he made and break. But today we're going to just test the Lyapunov stability in this system. And this system is pretty well established. So we can just use this function as our Lyapunov function. So x is a position, x dot is velocity, and this is a second order system, basically spring and damper, right? Question?
Relate to what we're doing in terms of feedback control.
Ah, good question. So when you're taking we're gonna do in this example, but because you asked it. So our system dynamics is going to be at the end, it's going to be x double dot is blah, right? F x and x dot t, right? If I define the Lyapunov function, by the way, this x is a state. X is x and x dot. Function mean this as the x t. Then when you're taking this time derivative, then you're gonna see the x double dot somewhere in this term. So when you plug in this to there, but this x double dot is also highly likely function of u, your control input. Then depending on how you formulate the control input, Lyapunov function can be negative or positive. So what I want to say, proof here is that if you just use the KP and KD, this PD feedback control, negative feedback control, then system is always stable. And yeah, let's go back to the example. So let's say that this is our Lyapunov function. First question, is this 0 at the origin? Right? Yes, right? Is this always positive other than 0, other than origin? Also true, right? So we already checked the two conditions. The last one we need to check is time derivative of this one is negative, right? So let's do this. Time derivative of this equation is this, right? M x dot x double dot plus what is that? B k, k x x dot. And what is the x double dot of this system? Here, this is second order system, so dynamics is mx double dot plus bx dot plus kx is 0, right? So my x double dot is minus b over mx dot minus k over mx. And I'm going to plug in these two here. Then it becomes x dot minus bx dot minus kx plus kx x dot. So now you can see it ends up with minus b x dot squared, right? So it looks like negative always, right? As long as b is positive. And we know that damper is always has a positive number, so it's negative definite. And then it goes, and when the b is 0, which means that the undamped system, then it's gonna maintain the energy. If it is anything larger than 0, then it's gonna converge to the origin, asymptotic stability. Question?
Basically, the partial.
Yeah, partial derivative t gradient with respect to the t.
We had the.
That in this shape, that gradient, you probably thinking about this arrow, right? That one is actually the state gradient. Any question? You can accept this? Okay, then system is stable, right? Okay, let me show this one. System stable means that any spring damper system, basically almost all the system you can see in the world is a spring and damper. It has some elasticity, but also has some damping. So then every system, every object in the world should be stable, right? Converge to the static state. Have you seen this video? Not always. Yeah, you saw this kind of video, right? So spring damper system is broken and it becomes unstable. And this one actually show that there is excitement and the excitement frequency is changing. And this is exactly spring damper system, right? And you can see that now it's moving up and down really a lot.
Amplitude is
Right?
massive. Looking at least 40.
It seems like it's diverging. If you do this more, then it's gonna
4.
grow out.
Oh,
So it's
oh dear. It's died off. 4.
okay. This means that spring damper system currently diverge. And why?
You're adding energy to the spring.
Mhm.
Every time it's like competitive.
Yeah.
So that everything adds the extra.
And you see the difference between this case and this case, right? In this case, you didn't do any except putting the spring and damper. I mean, in this case, in this video, they actually excite the system in a certain frequency. And as if this frequency is same as your system's natural frequency, then system blow out. So it's like this. System is oscillating. If your system moving in this way, you push this way. If your system going in this way, you push this way. What it means that it's going to slow down at the end, right? But if you push the system when it move this way and when it move this way, so it's just continuously pushing in a direction it move, then system going to blow up because you injecting the energy on the right spot and right time. And that right time determined by natural frequency. And that omega n has that idea. So that's a system natural frequency. Don't excite the system with this omega n. And the equation omega n was square root k over m, right? So what it means that if your system has a really stiff material, then you're gonna see the really high frequency as a natural frequency. So for instance, something like this, you cannot see that oscillation, right? Because most of the excitement you made is way below their natural frequency. But spring is different. Spring has a bit region over K. So then you can actually see that oscillation with your input. So if you do this, then this frequency is about 3 Hertz. The natural frequency of the steel is way above the 3 Hertz. So then it's hard to excite that system. There is a way to make this steel and all that kind of things excited. So you can actually, touch the natural frequency of the certain system made with a steel or more stiff material. How? Increasing the mass. So even though you have a really stiff bar, if you're putting really large mass, then you still can see oscillation. So it's a kind of the robot design perspective. So in case of the robot, you don't want to see the robot is fluctuating, right? This robot move this way, and you want to see the robot. But if the robot has moved this way and oscillating like this, then it's extremely hard to control, right? So then it always ends up with how light my end effector is and how stiff this structure is. Because your material need to be, thicker to make the system is more stiff. So normally you try to make a structure is as strong as possible, but at the same time it increase the mass. So at the end, you're gonna decrease the natural frequency, then your arm is oscillating. So this is one of the reasons why it is difficult to design the robot very well, because if you wanna make it stiff, then inherently you are increasing the mass. But this mass increase actually decreasing the performance of the system because you are putting the natural frequency down. So it's a always balance game. Okay, sum up. Practice system with a spring and damper. What it means that if the system has already friction, also has this elasticity, then system dynamics is m theta double dot plus b theta dot plus k theta. This is just natural damping and the natural stiffness. And this damper, in many cases in the robots, damper is a friction. So whatever friction in your drivetrain is a damper damper B. If you're engaging the KD and KP, which is your proportional and derivative feedback gain, then system dynamics goes into this way. So this is why when you increase the KD, you have to be careful because you already has a B, which is friction. So maybe system is already damped and you're adding the KD, what it means that you're gonna make the system is more damped. Depending on how you're setting up the KP and KD, it can be, it changes the steady state error overshoot at time constant. And what is the time constant? What is the state error? State error is the error you're gonna see when you wait a long enough time. So it's gonna end up with a certain position. We hope that it's converged to the desired at the end, but it's not always true. So it's maybe stop before it leads to the desired, or it does not come back from the overshoot. So that's the state error. Overshoot is overshoot. So if there is some state beyond the desired, then it's overshoot. Time constant is how quickly this system behaves. So it's like this. If the spring is strong, what it means that this one is strong, natural frequency is high, your system is responding really quickly. So it has a better time constant, a shorter time constant, but you're gonna see the overshoot in many cases. But it converges to the target very quickly. If the damper is strong, overshoot will be small. So you probably going to see the more gentle behavior of the system, but it converges to the certain speed slower. So that's the balance game again. Okay, if I wanna, so far we all about if there is the target, how quickly it goes to the target, right? If I wanna move the robot, so my target is moving, what it have to do is just updating the target every time. So desired target can be function of the time. And velocity also can be function of time. velocity is not desired velocity, not doesn't need to be always 0. Can I make system unstable? Okay, if I'm showing the video. So at the end, you're gonna apply this formula in your torque control, torque command. In the system, you are going to control the joint torque, right? And joint torque formulation going to be decided by this formula. Measuring the current joint position and velocity, calculating the error, multiply with the Kp and Kd, sum up, and that is the joint torque. And I say this spring damper system should be stable. I mean, it can oscillate, it can damp, but it doesn't mean that your system going to blow out, right? So then it means that even though you use the Kp and Kd a bit poorly set, system must not diverge. But sometimes, actually many times, you're gonna see the system actually does not follow your trajectory or blow out. I mean, this makes sense because even though it oscillated, but it eventually converged and stabilized, right? So let me show the same robot. They started from the 0, and this is my target. I go there and stabilize. Okay, this is definitely an underdamped system, right? So let me, can you see my, how can I increase? Oh, okay. Ooh. Ooh. Where is my KD? Okay, my KD is here. So you can see my KP is 250 and KD is 1. So it's way below the critically damped system. Let me increase to like 40. And then run the system again. And you already see that it's not, very doing something, right? It's not converging. Let's increase more. Actually, we can increase more to make system is damped, right? Because now it's doing even worse things. And it's still vibrating and doing something weird. So it looks like about to diverge, isn't it? And it's diverged. Why? I mean, it should behave like damped system, right?
Too much. So it's like panel living.
But even in the case, it should converge. It can oscillate around the target. Actually, because this is a really damped system, it should not diverge. It actually moves slower, and you're gonna see the state error instead of this vibration, right? And let me give you the time step. Okay, I'll give you the one hint step. Okay. So currently I'm using the time step, which is delta t. You remember the physics simulation, you integrating acceleration, right? Numeric integration. Let me change it to the 0.01. Instead of 1 milliseconds, I'm using the 10 milliseconds as my time step. And I run it. And it's even more unstable. So you got the idea. Sorry? Numeric error? Maybe. So I said a spring damper is not going to be unstable. It should be always stable because if there is no time delay. So our digital feedback controller can be unstable because you are not you cannot actually behave like an actual spring and damper. Actual spring and damper, which is spring and damper exists in a real world, that behave continuously, right? Time resolution of our real world simulation is infinitely small. But in the digital system, digital controller, maximum probably 1 milliseconds. 0.1 millisecond is really rare. Anyway, you're gonna have that kind of the milliseconds delay. And this digital simulation is actually not even close to the real world continuous dynamics. So the sensor data you've seen is in maximum 1 millisecond old data. And the control input you can engage is going to be applied to the system. After 1 milliseconds, you got that formulation, you got the result, right? So there is the time delay. If the time delay is more and bigger and bigger, then system can be more and more difficult to control. So that's why when I first setting up the dynamic simulation, this behavior is actually using only 1 as a KD. So when you increase the KD, even in your simulation, you have to be careful because it can blow out the system. And in actual world, it's actually even worse because you're gonna see all the noise in the velocity signal. Okay, one more thing. This is last. Normally, you do not command the position of the joint. Normally, you command position of the hand, right? You control the hand position rather than the joint position. I mean, the way we can get the hand position so far is computing the inverse kinematics. Then you can calculate the joint position. That's one way. You can do that. But we can also directly apply the feedback control in the hand. How? Well, we just made this force, right? So if there is a hand trajectory, if I want to make the robot following this circular trajectory, then x desired and x dot desired going to be defined by this r cosine t. And then making feedback controller. Then we can calculate the force the robot need to make, but at hand, not torque, not joint. So we made a force, and we know that if the hand make this force, then it's gonna follow this circular trajectory, right? But how can we find the torque generating this force? So we need a torque command at the end. So now, currently, this formula say that, okay, if you made a force with a Kp error and Kd error here, then it can move to this way, right? But I need to calculate the torque consistent with associated with this force. What's the formula? Yeah. Do you remember? We did this multiple times. You remember this slide, right? So Jacobian transpose F going to give us the tau. So then, I mean, let me skip this equation. Anyway, Jacobian transpose F going to give us torque. So calculating force in this way, Jacobian transpose give us tau. Let's say I have a Kp and Kd is a 50 and 10. So then let's increase the Kp and yeah, it's doing a bit better work, right? Why it is not perfectly following this?
Is it like fluctuate around the trajectory, like it try to?
Oh yeah, yeah, maybe, yes. But you can see the error is always a bit below than this circle, right? It's not exactly oscillating. It's actually below this circle. Let me show one more time. It's just a bit,
Because at first it's like overshooting, right?
That's gravity.
yeah, it's because of gravity. So now currently this force need to fight against to the robot's own mass, right? And actually it need to fight against with a Coriolis term as well, and its own mass as well. So because this system has its own dynamics as well, if we just ignore the everything and just put in the feedback controller, just hoping the feedback controller making this system follow the trajectory is actually too much demanding work for this system. There is a way to cancel out. So I'm going to use the same KP and KD, but with whole this equation. But then you're gonna see this nice tracking. Because this lambda mu rho is actually cancel out the system dynamics. And this is the idea of the operational space control, which we're going to learn next lecture. In practice, you have to think about the unknown friction, time delay, signal noise, and system can be, even in simulation, is unstable. It depends on the how you're setting up the system, how you're setting up your simulation. And this is a summary we've learned today. We're gonna learn operational space control and whole body control next week. Any question? What is the piece part of this? This is
Always feedback versus, yeah,
feedback versus the.
I guess you need feedback.
Yeah, we need feedback because without it, system not going to do anything, right? So we need feedback, but as you said, the computation time is also causing the delay. So it can be even more unstable because of it. Any other question? Okay, let's finish the lecture here.